In this video I'm going to show you some of the applications of differentiation to rates of change. So I'll just do a couple of examples. In the first one we'll look at calculating average rate of change with instantaneous rate of change. I will actually do it from first principles. Remember that at this stage you don't need to do that. And then we'll show you the shortcut. And then we'll look at a question that is more of a modelling and applied kind of question and have a think about what it means in terms of that context. So we can use differentiation to calculate the exact rate of change at a particular point on the function, which is the whole reason that we're trying to do this. But how does it compare with estimating from the average rate of change? So we sort of did this at the beginning of the chapter when we looked at average rate of change over a particular time interval and then looked at how that compared with the instantaneous rate of change. But there's a nice little question here that kind of wraps it all up together, so I'll do that for you and we can have a look. Okay, so we've got this function. F of x is x squared plus 2x, and the question asks to find the average rate of change for the interval 2 to 3, where between x is 2 and x is 3. Then the average rate of change for the interval 2 and 2 plus h, so that's where our sort of limiting chord theorem comes in. And then the instantaneous rate of change. So when you see average rate of change, what that means is gradient between 2 points. So gradient between 2 points. Okay, so that's just rise over run. When you see instantaneous rate of change, this means differentiate. Alright, so let's have a look at these first. So if we're doing this one, we need y values for these. So when x equals 2, y is just going to be 2 squared, 4, plus 2 times 2, 8. Okay, and when x equals 3, y is going to be 9 plus 6, 15. So this is therefore the gradient will be 15 minus 8 over 3 minus 2, which equals 7. So that's our average rate of change over that interval. Now let's have a look at doing this from first principles. So what we've got is the same sort of thing. We know the first point is this one, but the second point is when x equals 2 plus h, y equals, and now we're substituting into anytime we see x, we're putting 2 plus h squared plus 2 outside 2 plus h. So this is our x value, this is our x value. Okay. Now if we simplify that down, alright, you end up with 4, 2 squared, plus 4h plus h squared plus 4 plus 2h. Okay, so when we work out the gradient, we need to do this point, 4 plus 4h plus h squared plus 4 plus 2h, subtract the original, which is just, 8, over there, and then dividing by, and remember it's going to be 2 plus h, take 2. So 2 plus h, take 2, those cancel out. Okay, if we work this out, 4 plus 4 is 8, that will cancel that one. We've got 4h plus 2h is 6h, plus h squared, all over h, and if you factorise that out and cancel, you can cancel that with that one of those. Okay, so that leads to 6 plus h. And of course, as we limit h towards 0, so we say limit as h tends towards 0, therefore will be 6. Okay, so you can see it's a little bit less than that, but sort of in the same general vicinity. Alright, now the last one says find the instantaneous rate of change. Well, that means differentiate, so we're talking about f dash x. Okay, bring the power down, reduce the power by 1. Now we want to know what is that when x is 2. 2 times 2 plus 2 is 6. Voila! So much easier. Okay, this is why differentiation is fabulous. Alright, so it just makes your life a whole lot easier. So in terms of questions that you might be asked to do, you may be asked to do this. So just be mindful of average rate of change versus instantaneous rate of change. Okay, average means that you're finding the gradient between 2 points, and it's not going to be all that accurate. That's what you do there. You won't be expected to do this just yet. but it's good to have an understanding of how this works and how you substitute these values into here and use your limiting chord theorem. Okay, and then of course this is our preferred way because it only takes 3 lines of working and it gives you the same answer. Alright, so that's our differentiation. Okay, so there are many practical scenarios where, I should say finding, sorry, I think I was putting these together late at night, where finding the instantaneous rate of change of a function is useful. So one big one is velocity and acceleration, because of course if you differentiate a time displacement graph, you end up, so displacement, you end up with velocity. Okay, if you differentiate that, you end up with velocity, and then if you differentiate your time velocity graph, you end up with acceleration. Okay, and for those of you doing physics, you may have come across this already, and what you should find is suddenly all those physics equations that seemed a little bit random suddenly make a whole lot more sense. Okay, so that's where we like to tie in our maths and science. So what I'll do is show you a practical application, bearing in mind that whenever you're doing applications questions, you need to think about context. You need to think about what makes sense in terms of domain and range. So what values can I put into this function reasonably? What values can I expect out of it? When does it not make sense anymore? So typically we're talking about values that are positive or negative, but there are sometimes other restrictions. So we'll go through this and I'll show you what I mean. Okay, so we've got a balloon developing a microscopic leak and it's gradually decreasing in volume. So this is the function of volume given by time, so clearly it's negative, it's going to be decreasing for times greater than 0. So there's your first restriction, you're not going to have any negative time. So keep that in mind. Okay, so this is the volume at any given point. If we want to try and find the rate of change of volume, that says to me differentiate. Okay, so differentiate this function and then you can substitute in values of t, 10 seconds to 20 seconds. Okay, so the first thing we need to do is differentiate. We want dv dt, so the rate of change of volume with respect to time. Okay, that 600 is going to disappear. That's going to be minus 10. Be very careful. Remember those minuses. Any sign in front of the number stays with it, or in front of the term stays with the term. Okay, that will be 2t over 100. Of course, that cancels that and becomes 50. Okay, now when t equals 10, that will give us minus 10, take 10 over 50, okay, or just minus 10.2. When t equals 20, minus 10, take 20 over 50, or minus 10.4, sorry, not 5. So that's in centimetres cubed per second, so it's decreasing at a rate centimetres cubed per second, and you can see the rate is increasing. So as the volume gets smaller, the rate of reduction is increasing, so it's decreasing at a faster rate. Now the second question says, for how long could the model be valid? So if you're just looking at the derivative, well, it sort of seems like it could just go on forever because it's just increasing at a higher and higher rate. We always expect it to be negative, it's never going to become positive. So that seems okay. But if we go back and look at the volume, clearly at some point the balloon's going to empty and the volume will be 0, and the volume can't be less than 0. So what we're looking at is, as long as the volume is greater than 0, it could be valid, okay, and it might not be. It might change as the dimensions of the balloon change, but it's possible that this could hold, but it certainly won't hold for volume. We can't have the volume be less than 0. Okay, so it actually says for how long, so what we need to do is find when does that occur. Alright, so if we say 0 equals 600 minus 10t, take t squared on 100. Okay, and now using our nifty class pad, we can solve that. That's includes from last time. Okay, so we want 0 equals 600 minus 10, and I'm just going to use x, so I don't have to muck around with defining variables. Take x squared over 100. Okay, I'm just going to put that in brackets in case ClassPad does something a bit funny with that. Okay, now we need to solve that. But solve Good. Okay, so we've got a negative answer here, which clearly isn't right. Negative 1056.8. Okay, because we can't have negative time. But the other one was 56.8, and that seems reasonable. Okay, so for how long could the model be valid? Well, we've already said that it's only valid for t greater than 0, so the domain in terms of time is going to be t between 0 and 56.8. Okay. So, in the words of the mighty Alan Sadler, who has a huge amount of influence in terms of teaching of ATAR maths all across Western Australia, his favourite thing to say to students is, if in doubt, think. Okay, and although it seems sort of self-evident and fairly simplified, it's a really good little piece of advice. If you just stop and think, most of the time it'll become clear what you are trying to do. Okay, so when you're talking about applications questions, always have the context in mind. Alright, so you need to think about, what am I actually trying to model, what are the numbers telling me, what's going to make sense, what doesn't make sense. Okay, when you get results, don't look at it just as a number, look at it and think, what does that actually mean? Alright, so in the case before with the balloon, we had the volume decreasing at a rate of 10 cubic centimetres per second. Does that sound reasonable? Seems fairly reasonable. Okay, if you had a really large number, that might be a problem. It could indicate that there's something wrong in your calculations. Okay, so always think about, what do your results mean, and do they make sense? And if you always keep that in mind and you're always thinking, then hopefully you won't ever come unstuck.